Okay, hello everybody. I would like to welcome you back to May Institute on Computation and Statistics for Mass Spectrometry and Proteomics. Today we are focusing on R-based tools designed for mass spectrometry, and we're specifically looking a little bit under the hood and looking into the design of the software, design principles, and in particular, how we can work with raw data and how we can work with data that do not fit in computer memory. If you are joining us for the first time today, just in terms of logistics, at the bottom of your screen, you have two buttons, chat and Q&A. So chat is used for logistics questions, for example, if you cannot hear the speaker or if it is not clear where the materials are. But for everything else, for every question that you have regarding the actual presentation, please use the Q&A button, because this button allows us to manage questions more efficiently. And please do not hesitate to ask questions. We really hope that despite being, online and being separated, we can make this presentation as interactive as possible. So now let me welcome our second speaker for the session. So Kylie Bemis is a statistician by training. She holds a PhD in statistics from Purdue University, and she is now a lecturer in the Curie College of Computer Sciences at Northeastern University. And her research focuses on development of R-based tools and also statistical and machine learning methods for imaging mass spectrometry. And she has invested a lot of effort into working with imaging mass spectrometry data, which are, as we know, very large and require a lot of special design and special structure due to the spatial nature of the measurements. And so I'm very excited to have an opportunity to hear from Kylie today, and I hope you will enjoy the presentation. Thank you and welcome, Kylie.
All right, hello everyone. So I'm going to go ahead and start off with a couple quick polls to get a bit of an idea of who's in the audience. Originally, this was intended to be more of a developer-focused module /talk/tutorial, but with everything going online, I know our audience might have shifted a little bit one way or the other. So I'm just going to start off with a quick poll to get an idea of how familiar everyone is with R, developing R packages, and where they stand in terms of experience and interests. So you should be receiving a poll now, just asking you how familiar you are with R and developing R packages. So I'll just wait a moment while everyone answers that. All right, so it looks like we have a pretty good mix of some more beginners with R, along with some more intermediate advanced R users, and just a few people who have either written a package or are currently working on one. So I'll try to make some of this material a little bit more accessible and focus on some things that might be more applicable to the people who have a little bit less experience or who aren't currently developing an R package, but hopefully some of the things that I go over will be of interest to, if not everyone, at least most people. Next poll I'd like to give is just your familiarity with the Cardinal, the bioconductor package for mass spectrometry imaging. So whether it's new to you, you've just heard about it but not used it, or if you've used it a little bit or a lot, just to get an idea of your experience. All right, so again, a lot of people, it seems like a lot of people, this is their first time, either their first time hearing about Cardinal or their first time working with it if they've used it before. So I'll take some time to kind of introduce things a little bit in more accessibly and start from the beginning in some places. All right, so I've added some additional links. Oh wait, I need to share my screen. All right, so as Olga asked, please use the chat only for logistical issues. And if you want to ask me a question, ask it on the Q&A tab. I'll try my best to keep an eye on that. And if I don't get to some of the questions, Olga will politely interrupt me. So if you're coming to this now, I have added some additional links to the Google Docs document that's linked from the May Institute website. So if you follow this docs link, you'll see some basics in terms of materials for this kind of tutorial design talk / code walk, whatever this ends up being exactly. Just a second. Sorry about that. Oh. I did not mean to combine those. Bear with me one moment. Okay. So here I've added some links that will be helpful to you. Some of this we'll be using, some of it we won't go over. So I'm gonna primarily be discussing the design and implementation of the Cardinal package for mass spec imaging analysis. I'll also be talking a bit about the Matter package, which is a backend that Cardinal uses to work with larger than memory data. And I've provided some links here to the Cardinal and Matter landing pages on the Bioconductor project, which is a repository for bioinformatics-related R packages. And I've also included some links to the Cardinal vignettes. These are hosted on Bioconductor, and we'll be looking through a little bit of those to give you an idea of what Cardinal is and what it can do. Installation should be pretty simple. If you have R installed, just need to make sure you have the BioC Manager package installed. That's the Bioconductor installer. And then you can do BioC Manager ::install Cardinal to install the Cardinal package. And then if you want access to some of the example data sets that we'll be using from Cardinal workflows, make sure you install that as well. Some supplementary material that I'll probably be going over, since we have some people who are more new or less experienced with R, is I'm going to be going over a few slides from the intermediate R crash course that we had earlier this week, particularly some material on scalability, which was a topic that we didn't actually get to during that module due to time and everything being online. And for those examples, you may also want to install this MS example package that I have. This one's only hosted on GitHub because it's just intended for teaching, not for actually using, but it has some simplified examples of some R programming fundamentals. So you can, if you follow those links, there'll be installation instructions for those materials as well. So if you want to access everything from that intermediate R course, I have those materials all hosted on GitHub. You can follow the installation instructions in the README if you want to download and install the packages required for that. And for the MS example package, this is a pretty simple package that is intended for teaching some basic R programming concepts in the context of mass spectrometry. So you can install this using the remotes package. You can just do remotes install GitHub and then give the GitHub my username, Kuistilu, and MS example is the name of the GitHub repository. So I'll start off with just a little bit of background for everyone. So Cardinal is an R package on Bioconductor for analysis of mass spectrometry imaging specifically. So Cardinal's specifically for imaging mass spectrometry, it isn't really for analysis of traditional mass spectrometry or traditional proteomics experiments. For all of that, you should be using IMZML in combination with MS Stats. So this is specifically for imaging. But some of the programming R concepts I'll be talking about is hopefully more generally applicable if you don't work with imaging. This was a project that started, I want to say, roughly 7-8 years ago, and Cardinal was released officially in 2015. So Cardinal is turning 5 years old this year. And this is, when I started developing Cardinal, I was studying statistics at Purdue University, getting my PhD, and trying to design statistical methods for analyzing mass spectrometry imaging data. And at the time, there weren't really any R packages just for working with mass spec imaging data in general. And so there was a need to create a package that could actually work with this kind of data, from reading the experimental data files, doing pre-processing, and all of that nitty-gritty stuff before you could get to the statistical analysis, which was originally the main focus of my work. So that is where Cardinal kind of came about. And so some examples of using Cardinal. So this is the Cardinal 2 user guide vignette. So I can get to this just from the Bioconductor Cardinal page. So all of the packages on Bioconductor have vignettes and documentation. So I just followed this HTML link to this vignette, and I'm just going to walk through some basics of what kind of how to get started working with Cardinal. So here I have my RStudio set up. So I'm using R 4.0. So this is the newly released version of R that came out a few weeks ago. And so I'll be using the most recent version of Cardinal that was released with Bioconductor 3.11. So if you use an earlier version of R, you'll be on an earlier version of Bioconductor. So things might work slightly differently, but not too differently. So if I load Cardinal, just with library Cardinal, it'll load a few other packages that are the requirements. And I'm going to go ahead and, let's say, actually going to get a sample data set from the Cardinal workflows package. If you don't have this installed, in the main Cardinal vignette, there's some examples using a simulated data set. So you could follow along using that if you don't have access to Cardinal workflows. It is a little bit of a download, but I'm going to load this PIG 206 example file from the Cardinal workflows data set, or from the Cardinal workflows vignette. And get the corresponding vignette for that. So this is a if I take a look at what this is a MS continuous imaging experiment. So Cardinal has a few different classes for working with different kinds of mass spec imaging data. There is a general class called MS imaging experiment. And then there are two subclasses of MS imaging experiment called MS continuous imaging experiment and MS processed imaging experiment. And depending on what kind of IMZML file you load, you'll get one of these two. So I'm going to, again, back up a little bit and talk very briefly about the IMZML format. So as you know, when you're working with mass spec imaging data, you can get many different kinds of data files from the mass spectrometer. And in order to actually work with these open source tools like Cardinal, MSI Reader, and so forth, you have to convert them to IMZML, which is a really nice open source format based on MZML. but with some modifications to make it more appropriate and efficient for mass spec imaging. So Cardinal is designed, or at least the latest versions of Cardinal are designed very closely around the IMZML format. And so in working with mass spec imaging data in Cardinal, it's going to be useful to understand a little bit of this IMZML format. Not in a great amount of technical detail, but just to understand that IMZML is actually there are actually two variants of IMZML to be aware of. So IMZML, there are a lot of converters from the raw instrumental files to put something into IMZML, available from the imzml.org website. And basic IMZML has two different files that it will actually make. There is an XML part of the file, and this is going to be all of the metadata associated with the experiment. So it'll keep track of things such as what was the instrument that was used, what kind of ionization was done, the spatial coordinates of all of the pixels and mass spectra, what kind of spectra they are, either profile or centroided, that kind of thing. All of the experimental metadata is stored in this XML file, which is designed to be somewhat human readable. But this is where all of the metadata for the experiment lives. Then you have a separate file called the IBD file, and this is the imaging binary data. So this is where the actual intensities from the mass spectra are stored. So IMZML separates the experimental metadata from the actual intensities of the spectra to both make it more efficient and also to keep the metadata neat and tidily separated from the actual intensities. So whenever you're working with IMZML, you'll have these two files. One will be .imzml, the other will be .ibd that you'll be working with. Now, IMZML actually has two variants to it. And just looking at the files on their own in your file storage, it won't be immediately apparent what they are. But when you read them into Cardinal, you'll be able to tell what kind they were. And so there is a processed IMZML format and a continuous IMZML format. And the processed name here is kind of a misnomer. It doesn't actually imply that any sort of spectral pre-processing has been applied to the spectra. It actually just is referring to how the data is actually stored. In a processed IMZML file, each spectrum can have a different array of mass to charge ratios, a different array of MZ values associated with it. So in a processed IMZML file, each spectrum can have a different list of MZ values. Whereas in a continuous IMZML format, all of the spectra will share the same MZ array. All the spectra will share the same mass to charge ratios for all of the spectra. And so generally when we're working with MS imaging data, the continuous format is going to be much easier to work with once we actually want to do some sort of statistical analysis. However, lots of times the data will come in this processed format, which is efficient for storing the raw initial data, but it's not as easy for doing statistical analysis on because each spectrum has a different list of MZ values. Now, when you get these into Cardinal, there is an MS continuous imaging experiment and an MS processed imaging experiment class that is associated with each of these, and they behave differently. So for example, PIG 206 here, this is an MS continuous imaging experiment. And so one of the properties of that is it's going to be really fast to plot an image. So here, if I want to plot one image from this PIG 206 with MZ 888, that's quite fast. Let me load up an example of a processed file. So I'm going to grab an example of a processed IMZML file. And I'm going to use an example that's actually on the IMZML.org website. So if you go to example files on the IMZML.org website, there are a list of example IMZML files that you can play around with. I'm going to use the first one here that has a publication associated with it. This is from the PRIDE database. This is slightly larger than the other example files. The rest of these are really quite small. But I'm going to be using, I'm going to take a look at this one. This one's 815 megabytes. You can download it from the PRIDE repository if you want to. So I'm going to, let's see, what's the best way for me to, give me, no? Let me, so I'm going to give myself the, make a string with the path to this. Copy. All right, so now file has the name of this IMZML file, which I happen to know is a processed IMZML file. And in Cardinal, there is a function called read MSI data. And I'm just going to load this IMZML file using read MSI data. Now, because this is a processed IMZML file, each spectrum has a different list of MZ values associated with it. And one abstraction that Cardinal provides is you are always able to access the data as kind of a data cube. So if you want to index a particular mass to charge ratio, then you're able to do that. To do that, we have to have the data represented as a matrix, and that means I need to know the mass range and the mass resolution of this data set before I can actually do anything with it. If I do read MSI data without providing a mass range and resolution, Cardinal will go through and try to figure out an approximate mass resolution and the mass range from the data itself, which is why it took a little bit of time to process this before actually reading it in. So it says detected mass range 400 to just under 1,000. Estimated mass resolution was 10 ppm. Let's see. I have a question, but for some reason it's not.
Kylie, I can read it out to you. For the continuous files, how is the M over Z axis aligned?
For continuous files, how's the MZ axis aligned? So that that kind of depends on. There's really no way of knowing that without looking at the IMZML file itself. You can check to see what the mass to charge ratios actually are. But whether they got that way from some kind of pre-processing, peak picking, and alignment, or whether they got that way just from how they were recorded off the instrument, that information you would have to look there. You would have to check if the IMZML file contains that information. So, for example, this PIG 206. This came from, this is a relatively small data set, but this came, I believe, from a Thermo LTQ instrument, and it was originally in Thermo raw files that was then converted to analyze files back when we used to use those more often, and then eventually, this was actually never originally in IMZML, but it is now stored as an MS continuous imaging experiment. So I could see the mass to charge ratios here if I wanted to, but this is just the raw profile data as it came to me from the THOMO raw to the analyze files to me. And I'm not sure what exactly was done in terms of when this file was exported from the instrument software. So that's the kind of the best I can answer on that. We would store files in a continuous format really anytime when it's convenient to store the data like that. So ideally, we would get data into that continuous format before doing actual statistical analysis, because then it's much easier to access that data as a regular matrix. So here, in this case, this continuous MS imaging experiment happens to be the full profile data, but it could also happen to be a peaked picked data set that has aligned peaks. And actually, there is an example of that in the Cardinal Workflows package. So here, PIG 206 peaks. This is also in the continuous format, but now with just 143 features, because this is a version of it that has been peak picked and centrated. Okay, to go back to this other example file that I just loaded. This is this first file from the IMZML.org website. I believe it is a mouse bladder. And so this is a processed version. And as part of Cardinal's abstraction, it is represented as a 91,630 MZ features by 34,840 pixel matrix. And so that means if I wanted to index into this and say get the image associated with the first MZ feature, I could do that just like this. Well, that actually returns a MS processed imaging experiment, but I could actually access this as the spectra. Although since I index by row, this is giving me gonna give me the image. So some things to consider when first reading this in is if you know the mass range and resolution beforehand, then specifying those makes reading the data much faster, because then we don't have to go through and look at the actual intensities and mass to charge ratios to estimate the mass range and the mass resolution. So here, if I do the same operation again and say I know the mass range is 400 to 1,000, and I'm going to use a resolution of 10 ppm, it's going to be much faster because now it can just use what I input and return immediately without actually having to look at the data. So much like the on-disk MSN set or on-disk MSN experiment, read.msi data does not actually load the data into memory, but rather keeps it in the files and accesses them only when necessary. So here, if I want to plot a mass spectrum, let's say from the 500th pixel, I can do that like so. And this data is only actually accessed on the fly when I want to plot it, rather than always being in memory. Now, there's a few different aspects of any MS imaging experiment object that I want to talk about a little bit before we move on. So, components of an MS imaging experiment, you have the pixel data. This is going to be all of the metadata associated with the individual mass spectra. It's called pixel data because in an MS imaging experiment, each mass spectrum is associated with a particular pixel location. So the pixel data has the pixel metadata information. If I do pixel data MSE, that returns to me a position data frame, which is just like a data frame, but it has additional annotations for the pixel coordinates as well as the experimental run. By default, this run assumes that each separate IMZML file is a separate experimental run, where a run is basically just a single slide. Let's see, we have another question. How to zoom the mass spectrum with plot. So when I'm plotting a mass spectrum, this works pretty similar to the base R plot function. So it takes an xlim argument that defines the limits of the x-axis. So I can just give particular limits here. So suppose I want to look at 550 to 600. Then I can do that. Let's look at, zoom into 580 to 590 to look at this set of peaks here. So that's how I can kind of zoom in along the MZ axis. And if I wanted to change the intensity axis, I can do that with ylim since the intensity is on the y axis. So here, let's go 0 to 15,000. Do images have to be rectangular or can they be irregular ROIs? So when we're reading, the IMZML doesn't require that the images themselves be rectangular. However, IMZML does require that each of the pixels have a gridded pixel position. By that, I mean IMZML, the specification expects the X, Y, and potentially Z coordinates are integers. Cardinal itself doesn't care. The recent versions of Cardinal can support non-gridded pixel positions as well. So they can be the X and Y positions of the pixel data can be floating point. They can be essentially anything. It will work best if the X and Y coordinates are gridded pixel positions, but it will try to make its best guess and work as well if these are floating point or decimals as well. As for whether the shapes can be irregular, yes. So for example, PIG 206, let me see if this has the full, yeah, so for example, PIG 206, the only pixels that are actually stored are the ones that you see that have a color. This particular data set has already been cropped so that most of the background is missing except for the pixels that actually correspond to the sample and maybe a small amount of background around the sample. So both IMZML and Cardinal have no problem with that. It'll work based on whatever the actual given coordinates of the X and Y in the pixel data position data frame actually are. Let's see, what did that question? Okay, so components, we're talking about the pixel data. So this has information about the X and Y coordinates as well as the experimental run. And if we had some additional information about each of the mass spectra themselves, this is also where we could store that information. For example, let me grab another set of data from the Cardinal workflows package. So I'm going to take a look at another set of examples. This is from, again, the Cardinal workflows package, and I'm going to take a quick look at some renal cell carcinoma cancer data set. So this is 8 experimental runs. In each run, each of these slides has a tumor and a normal tissue. you'll notice I'm coercing these to an MS imaging experiment with as. I'm doing that because earlier when these data sets were originally stored in Cardinal workflows, they were using a different format than MS imaging experiment. So I'm converting them to an MS imaging experiment as I'm loading them right now. So this, for example, if I look at the pixel data of this RCC experiment, there is an additional metadata column in the position data frame in the pixel data called diagnosis. And that's because some of the pixels here, some of the mass spectra have a diagnosis associated with them of either tumor or normal tissue. There is also a feature data. So this accesses the feature information. And this is essentially, by default, this is usually just going to be the list of MZ values associated with the data set. Now, when I was talking about processed IMZML, each spectrum can have a different set of mass to charge ratios, a different set of MZ values. But when we're actually representing the data in Cardinal, we want to be able to represent it as a matrix so we can easily slice an image in addition to extracting mass spectra. And so that means in order to actually plot images efficiently, we need to be able to have kind of a canonical list of MZ values that apply across the whole data set, even though each spectrum has a different list of MZ values associated with it. And that's done with on-the-fly binning based on the mass resolution given to read MSI data, or the resolution that read MSI data calculates. So here, this mouse splatter data set has, we're using a 10 ppm resolution, and so that resulted in 91,630 mass features. That happen to be these ones. However, if I don't like that, I can actually change it. So here, let me change this to 15 ppm. That'll result in a wider bin size, so a bin size of 15 parts per million. And now this data set has only 61,086 features associated with it. So the feature data of a processed imaging experiment will update automatically based on whatever resolution there is. And then all of the spectra will be binned on the fly to whatever bin width is associated with that resolution. The actual data in the IMZML files is not changed by this. This only happens when we're actually either plotting the data or accessing it in some way. The actual underlying data does not change here. And then lastly, there is an image data. And this stores the actual lists of the intensities in a way that is accessible as a matrix. A shortcut for getting the actual spectra is this spectra accessor. And you can see for this mouse splatter data set, this is represented as a sparse matrix. You can see the MZ values that are associated with each of the rows here. So if I wanted to extract a single spectrum, I could do that by indexing the columns of this matrix. So in the case of, by default in Cardinal, whenever I read a data set and it is represented, and I do it without reading the data into memory, which is the default. So there is a argument called attach.only by default, this is set to true. That means by default, the data files are only attached. That means that the data is not read into memory. And when that happens, the spectra are stored using data structures from the matter package that allow us to access into these IMZML files whenever we want to without actually loading them into memory. Question here. Okay, so the image doesn't appear to be fast, and that is going to be true whenever you're working with a processed imaging experiment. And the reason for that is the spectra are stored based on the mass. The mass spectra are stored essentially as columns of a matrix. And accessing individual intensities from the file across every single mass spectra is going to be inherently slower than accessing a single spectrum. Doesn't appear within a for loop, appears to work well at a single ion at a time. While this is most true with the processed imaging experiment type, it will also be true to some extent with the continuous imaging experiment type while the data is stored on disk. If you have, and after you actually process the data and do peak picking, or if you load it into memory as a dense matrix, then plotting images will be much faster. This is just a consequence of how the spectra are actually stored in the IMZML file. The IMZML file, the binary part of that file, is set up such that it is very fast to access a spectrum, but it is slow to access an image. Part of that is just because of how the file is actually stored, and part of it is, in the case of the processed imaging experiment, also because the mass spectra have to be binned whenever you're creating an image. So that is an additional source of slowdown. So if you want to plot images fast, then having it as a continuous, converting it to a continuous imaging experiment, either by processing it or just turning the binned version into a dense matrix are two ways of doing that. So for example, let me take this mouse bladder data set. Let me check what a interesting MZ value to look at here. I'm not sure what MZ values these are. Let me just try one. So this is one example. You can see that accessing the image is a lot slower than accessing the spectrum. And that's because this one is a bit of a larger file. Well, not a large file in general, but a larger file than the pig data set. Okay, so that produced an image. Doesn't happen to be anything there, but that took some time. Now, if I wanted to, there's a function currently called collect that will pull the data into memory. And I can also request that it pulls it into memory as a dense matrix if I want to. All right, in the current version, that has been renamed to pull. This one has two. Let me change the resolution of this just so I can try to do this as an example. So currently this is pulling all of the data into memory and converting it into a dense matrix, which will take some time as the original version is sparse. And this is something that pre-processing the data would fix, because once we have actually pre-processed the data and peak-picked and centroided it, then it's really easy to store it as a dense matrix, and everything would be faster at that point. As an example of that, all right, MSC. All right, this is now a continuous imaging experiment. So now if I look at an image here, that's going to plot much more quickly. Let me see if I can find something that's interesting. I don't remember what the interesting MZ values for this data set are. But let me quickly show an example pre-processing workflow, but then I'm going to talk about some parallelization information. All right, so I'm going to take my pig data set because it's a smaller data set, so I can run things interactively here. I'm going to use this summarize features method to calculate a mean spectrum. Let me turn the messages back on. So this is what the mean spectrum for this data set looks like. I can also summarize over the pixels. So for example, here, this is getting the TIC, total ion current, for every pixel. So this is a plot of the TIC. And so when you're processing when you're processing an MS imaging experiment, we can do it using this piping operator as Laurent showed. The Cardinal workflow is going to be slightly different than the MSN-based one, of course. So here I'm going to take the mean spectrum object that I created, do peak picking, alignment, and filtering, and output this as a reference that I can now use to bin the rest of the data to. So what I've done here is I've created a reference. I've done peak picking on the means, just on the mean spectrum. You can also do peak picking on every individual pixel. But here, just for time, I'm just going to do it on this mean spectrum with a signal to noise ratio of 3. I'm going to align them to the local maxima of the mean spectrum. And then filter here will just remove the peaks that appeared in less than 1% of all of the spectra that were inspected. In this case, there's just one, so it's just going to remove the peaks that were 0 if there are any. With that done, I'm going to go back to the original data set. So these are the profile spectra. I'm going to normalize bin to the peaks. So I'm going to use the MZ values from the reference that I just created and then process these. And so the result of that is a MS continuous imaging experiment with just 110 peaks. And so now working with this reduced experiment, plotting the images from this will be much faster than if I were trying to plot the images from the full raw data. As a question, would you recommend performing peak picking alignment filtering on the raw data or after normalization, baseline correction, smoothing? So the question is when to perform peak picking, alignment, and filtering. And this is generally done after you have done normalization, baseline reduction, and smoothing. So in this case, I didn't bother to do any smoothing of the spectra or removing baseline because this particular data set doesn't really need it. Whether you need to do smoothing or baseline reduction depends on your data set. Obviously, if your spectra have a baseline, then you need to handle that. Some data sets don't really need to be smoothed, but generally speaking, if you're doing any sort of peak processing, either picking the peaks or aligning them, that should be done after you have done the normalization, smoothing, and baseline reduction. And I could do that, for example, here. So if I want to smooth these, I could do that here if I wanted to. It's going to take a little bit longer because we're now smoothing each spectrum before binning them to the peak reference. All right, so now something that I want to talk about, let me check, how am I on time? We're at 1:30, okay. And it's a question, there's a question, what's the difference between peak bin and reduced dimension? So in older versions of Cardinal, there is a method called reduce dimension that worked on an MS image set. Newer versions of Cardinal use an MS imaging experiment object rather than the MS image set, and the reduce dimension method is no longer used. So what peak bin here does is it uses a list of reference peaks. This can either be something that was generated from the data set itself or a list of external reference peaks. And then it kind of essentially goes down the bound and finds the boundaries of the peak and bins the intensities based on those peak boundaries. So reduced dimension is an older method for an older class. And while Cardinal has been in development over the last 5 years, much like Laurent added the on-disk MSN experiment to MSN base, a lot of changes have had to be made to support the newer better instrumentation and higher resolution experiments. And so the MS imaging experiment class is a reflection of that. And there's a slightly different workflow now. Image appears to be pixelated. Can there be interpolation or smoothing? So there is no interpolation done. And in general, I would advise not to, if you're using other software that does interpolation, I would advise turning it off, because then you're essentially creating data and you're not entirely sure where the original pixels are. However, there is smoothing. So let me take my Pig 206. Let's look at 888. And if I wanted to smooth this, there's two smoothing methods that are pre-implemented. There's either Gaussian smoothing, and so all this does is it passes a Gaussian kernel filter over the whole image. There is also what's called adaptive smoothing, and this does bilateral filtering, which is a kind of smoothing method that tries to preserve the edges better. Is it possible to image the number of peaks for each pixel? So we can do that if we want. I don't have a quick way to show you since right now I haven't done peak picking on the whole data set, but let's suppose that I did. It shouldn't take too long since this data set is relatively small. So where is that coming from? All right, so what I'm doing here, Pig 206 was my full data set again. I'm doing peak picking, but on every single pixel. Then I'm aligning them. Since I'm not providing any kind of reference, this will use the mean spectrum. Then I'm doing peak filtering. So this will remove low frequency peaks already. And now I take a look in the feature data here, or not in the feature data, excuse me, in the pixel data. So you can use, one quick note, you can use P data and F data as shortcuts for pixel data. Oh, wait a second, the question again. Image the number of peaks for each pixel. Oh, I see. Okay, so for that, you would want the number. Excuse me. I was accidentally calculating the number of the frequency of each peak that was detected rather than the number of peaks per spectrum. So just to finish this example, if you're interested in the feature data here, after I did the filtering, you have a column for the count, the number of times that peak appeared in the data set, and the frequency. So if I wanted to get the number of peaks per pixel, so currently, to do that, what I could do is use pixel apply. So this is a variant. This is, if you are familiar with the apply function from base R, this is going to essentially apply some function over every column of the matrix, so for every spectrum. And I'm going to, let's see, sum up the number of times that something is non-zero. Oops. And so now NP is now the number of peaks in each spectrum. And if I want to look at that, I can do that like so. So a lot of peaks up here in the back fat, it looks like. Okay, oh my, quite a few questions. Have to a reference to align the peaks. How can I use the reference? Is there a specific code? So if you have a reference to which to align the peaks, you just provide the ref argument to peak align. Here I provided a string, which means it's in a column in this data set. But if you have just a numeric vector of MZ values, you can provide that to this ref argument here. So if we have multiple runs, multiple tissues per slide, I think using the same peak ref from one tissue for different slides can introduce bias. Yes, so So if you are doing some kind of classification, if you want to apply a classification algorithm, when you're doing statistical analysis, then you do have to consider that the pre-processing that you apply to your training and test set should be independent. So you shouldn't be using information from your test set when you're training the data. In Cardinal, there is a cross-validate method that allows you to do separate pre-processing for the different folds while you're doing cross-validation for classification. I'm not going to go into the details of how to do that now, but there is an example of that in the vignettes. Is it possible to extract area under the curve of a feature while comparing normal and diseased tissue? So again, I don't want to go too in depth on specific examples here. So by default, there isn't a built-in method to extract an ROC curve for classification. If you wanted to, you can get the probabilities from most of the classification methods that are provided. So if you wanted to get the probabilities of those, you could plot an ROC curve yourself. Okay, so that's kind of some Cardinal basics. What I really want to do now, though, is address some kind of scalability issues. And so I'm going to go over and use some of the material from the intermediate R crash course that we didn't get to in that course. And these are things I'm going to talk about working with parallelization in R. And this is something that is going to be useful whether you're working with Cardinal or MSM-base or any or most other bioconductor packages. As Laurent mentioned, MSM-base uses the BioC parallel package for parallelization. Cardinal uses the same package. So I'm just going to talk a little bit about the BioC parallel package and what it does. So in this example, I'm going to load a simple IMZML package. So this is a simple package that I have hosted on GitHub that is a very simplified version of a way that we could store mass spectra. And I'm just going to simulate some mass spectra. In this case, it's not an imaging data set, but this is just a list of mass spectrum objects. And these mass spectrum objects are a class defined in this IMZML data set, or IMZML package, excuse me. And this spectra variable here is essentially just a list of 500 spectra that I've created or simulated. For example, if I plot one of these, it looks something like this. And this is just a toy example that I want to show you to show you what using this BioC parallel package is like, and some of the kind of things that you have to consider. Both Cardinal and MSM-base will do some of these things automatically for you, but being aware of what's actually happening in the background can be useful if you run into issues with kind of the default parallelization. So here I'm going to suppose that we want to apply some sort of processing to this list of 500 mass spectra. These are some methods that I have from this IMZML package called smooth noise, remove baseline, find peaks, etc. So for example, here is a smooth version of the same spectra. It doesn't actually look much different. Here is a peak-picked version of this particular spectrum. But suppose I want to apply this sequence of pre-processing to each of these 500 spectra individually. And in base R, the function we would use for that is lapply. This just means I'm going to apply some function to each element of this list. And I'm going to, the result, and it's going to be returned, the result is going to be returned as a list. And if I just do that here, I'm going to use system.time to see how long this takes. This took about 6.69 seconds, which is fine if this mass spectral list is relatively short. The question is, how well would this scale if we wanted to process maybe millions of spectra, or at the very least several thousand or tens of thousands? And so the easiest problems that we can parallelize are what's called embarrassingly parallel. And this is when the tasks that we're doing are all independent and don't require any communication between them. That's essentially anything we can do with this lapply function. So processing millions of spectra is something that we can easily do in parallel because it is an embarrassingly parallel problem. And I'm going to show you an example of doing this using the BioC parallel package. And this is essentially what Cardinal and MSN-base are doing under the hood. And it'll give you an idea of what some things you should consider in terms of how you're using parallelization, or if you run into problems with the default parallelization. So I'm going to load the BioC parallel package. And by default, there will be some number of registered parallel backends. So on Mac, Windows, and Linux, you might see slightly different parallel backends. So for example, on Windows, either you won't have what's called the multi-core backend, or it will just be a stub for the serial backend. There's also what's called the Snow backend, and the serial backend is what happens if you're just running things serially without using parallelization. So I'm just going to go over each of these backends because these are things that you can register and use if you're using any package that uses this BioC parallel package. And that includes things like Cardinal and MSN-base. Something in chat. That question I already answered here. Okay, so these backends. So the serial backend that you can create using serial param, this is a backend that just performs serial evaluation. By serial evaluation, I just mean everything is executed in sequence. So nothing is happening in parallel. This is useful if you don't want to run things in parallel because sometimes parallel evaluation in R can potentially be a little bit buggy. Or it might not be worth it in certain cases, and we'll talk about those cases. So that is the serial backend. On Windows, your default parallel backend is what's called Snow, the Snow backend. Snow stands for a simple network of workstations. And the way this parallelization works is that your host R process, so the R session that you're using, will create additional worker R processes. And these might be on your same machine. If you have a computer that's connected to other computers, then you could potentially create a Snow cluster that is spread across multiple machines. So R creates worker R processes that are fresh and new R processes, and it communicates with them via what are called socket connections. These are essentially network connections to those new R processes. One thing to consider when using this backend, which is, I believe, the default on Windows, is that because this works by starting new fresh R sessions, there is a significant amount of overhead associated with starting one of these clusters. And if you have data in memory that is required for the computations, that data has to be sent to the worker R sessions via these socket connections. So you have a good amount of overhead associated with working with this Snow backend because those new R sessions have to get started, and then you have to send data to them. Sending the data to them is mitigated a little bit by working with file-based backends like Cardinal and MSN-based do by default. But that can also cause problems if, for example, you're working, if you're trying to create a cluster that includes multiple machines. But there's a good amount of overhead associated with this. So this should really only be done if your data set is actually large enough that the amount of work saved by parallelizing it is greater than the amount of overhead associated with starting those new R sessions. On Mac and Linux, you'll also have what's called the multi-core backend. This is a backend that works by forking the original R session. Forking is a operating system command that essentially just clones, makes a copy of your original R session. What that means is each of the cloned R sessions have access to the same data set and already have all of the packages loaded that they need. So typically using this multi-core backend, if it's available to you, will be a lot faster than using the Snow backend. Again, this is only available on Mac and Linux. So unfortunately, Windows users either have to use the Snow backend or do things in serially. There are other backends that BIOC Parallel supports through the use of other packages. So Revolution R has a series of packages called For Each and Do Parallel, Do Snow, different kinds of do packages. You can register those backends with BIOC Parallel using the do par param. And there's a batch tools package for working with high-performance computing clusters that you can also use with BIOC Parallel using this batch tools param. But as an example, so here you can register a default backend for use with BIOC Parallel using this register function. So by default, Windows, I believe, will use Snow, Mac will use multi-core. But if you want to fall back instead to serial execution, you can register the serial backend. And once you've registered a backend, that will then go to the top of this registered list of parallel backends. And this BP param function will return the currently registered parallel backend. Now, BIOC Parallel provides a function called bp-lapply that is essentially just a parallelized version of the lapply function from base R. So this works just like lapply, but it will then parallelize the computation over whatever the backend that you're currently using is. And the default is to use the currently registered backend. And so as an example, here I'm going to use this backend. I'm going to use the serial backend. I'm going to change my lapply call to bp-lapply. And I'm going to do the same computation, smoothing, removing baseline, and finding peaks from this list of 500 mass spectra. And doing this serially using bp-lapply will actually take slightly longer than regular lapply because bp-lapply, as a special parallelization function, does have to make some allowances for the possibility that this might be in parallel. So here it took 12 seconds to do that. And if I plot the first result from this, I can see I have some kind of a peak-picked spectrum here. Now, if I want to create a Snow cluster with 4 workers, this is how I could do that. So someone wanted to know last session how to use all of their cores. So in BIOC parallel, there is a detect cores function that will detect how many cores you currently have. By default, BIOC parallel will create new parallel backends using all of your cores, but you can specify how many workers you actually want when you're creating them. So here I've created a Snow backend with 4 workers. I could make one with just 2 workers if I wanted to, or I can make one with 8. That's not going to help me since I only have 4 cores here. So I'm going to create this Snow backend with 4 cores. And now I can run this same code still using BPL apply, but now I'm going to change the backend to Snow, to this Snow backend I created. And I can do that by passing this BP param argument to BPL apply. One modification I've made to this code here is I've added a require function saying that I need to have this MS-example package loaded. And I'm doing this in here because SnowParam, remember, starts fresh new R sessions. That means the workers that are being created with this SnowParam backend don't have the same packages I have loaded as I do in my main R session here. So I need to make sure I have those packages loaded. And then when I call BPL apply, BPL apply will do the work of transferring the data to those workers. So here, let me see how long this takes. So Snow backends have a good amount of overhead associated with them because they have to start those additional R sessions. One thing to keep in mind is that sometimes, because the communication between these R sessions is based on socket connections, depending on the network settings of your computer, that is sometimes a source of bugs when trying to run things in parallel. All right, so you can see that that took quite a bit longer, actually, even though I was running things in parallel. And again, that's because of the overhead associated with Snow. In this case, I only have 500 spectra in my spectra list. So in this case, the overhead associated with using parallelization wasn't actually worth it. However, if I had, say, 5,000 or 50,000 mass spectra here, then possibly the overhead of starting those additional R sessions would be worth it from the time saved in terms of splitting up the work. In this case, just starting those additional R sessions kind of dominated the amount of time that I spent. Now, since I'm on Mac, I have access to this multi-core backend. So I'm going to create a multi-core backend with 4 workers. And so this should be a lot faster than the Snow backend. And this happened in only 6.4 seconds. So that was quite a bit faster than the Snow backend, which was 27 seconds. And also faster than the serial version using BPL apply. It ends up that it was about the same amount of time as just using the base R lapply. Again, that's because BPL apply is a more complicated function than the lapply function from base R. But here we can see that the parallelization did actually make a difference. So here, I cut the time in half, essentially, compared to the same call that I did serially. In this case, the data set is still small enough that I don't see a major improvement, but it was faster than just running the same code serially here. So some notes that I have on using BIOC parallel, and again, this is something that's used by a lot of bioconductor packages, including Cardinal and MSM base. Actually, these are more for developers, so I'm going to skip over those for now. But generally speaking, if you run into problems based on parallelization, it can help to set the serial backend and try running things serially, because it's not always going to be worth it to run things in parallel, as we just saw right now. And this was actually a problem for a while with Cardinal, because lots of times the default in BIOC parallel is to have some kind of backend by always. So the default on Windows was snow param. The default on Mac is serial param. And users didn't always know to turn this option off if they run into bugs. And it lots of times there can be bugs that are associated with just trying to run something in parallel. Again, particularly sometimes your computer will block the socket connections that it's trying to make to the additional R sessions. And so that's something that you should look into the documentation of this BIOC parallel package to try to figure out. But something that has been changed in the current version of Cardinal is now Cardinal has its own backend associated with it, separate from the registered list of parallel backends from BIOC parallel. So the default with Cardinal is now to use the serial backend, and that's just for stability and avoiding bugs. And because Cardinal doesn't always know whether you're working with a data set that will actually benefit from parallelization. So in Cardinal, you can set the Cardinal backend using set Cardinal BP param. And so if I wanted to switch to a multi-core backend, I could do that by changing this to the multi-core param, for example. And now if I went, let's see, and say wanted to do the same pre-processing, but now using this multi-core backend, I could do that. And now this is running in parallel, whereas before it was running serially. And so you can see when I was running this, since I'm running this in parallel now, all of these console output processing these chunks kind of appeared immediately rather than sequentially, because the workers finished kind of at the same time. You can also see that this isn't done in order. So here, the chunks 11 through 20 were processed before chunks 1 through 10 of the data. While in this second set of processing during the alignment, these were processed in order. After the processing is done, everything will be put back into the correct order, but that's just showing you that this was done in parallel. So some of the data was processed out of order because of that. All right. So the next thing I want to talk about is in terms of scalability. So I'm going to talk a little bit about the Matter backend package that Cardinal uses, as well as some other options that Bioconductor provides for working with larger than memory data. So here I'm going to, again, create, oops, close this. I'm going to create some spectra. In this case, these ones have a baseline. I don't know why I didn't have the previous ones with a baseline, but so here we have some simulated spectra that happen to have a baseline. And so when you're working with parallelization, because of those overheads associated with it, this is one area where working with file-based data. So either in Cardinal, this is the default, and MSN-based, this is also the default, to use the on-disk data rather than to load them in memory. And part of the reason that that is a good idea is not just because it's faster to load the data, but also because if you're running things in parallel, you don't have to transfer all of that data to the other R workers. So in general, most R functions expect the data to be in memory. And working with things in parallel makes this issue much worse if you're working with large data in memory. And this is especially apparent when you're using parallelization, because if you have all of the data in memory, when you transfer that data to the worker R sessions, you're actually going to be creating copies of that data. So you're going to end up with at least twice the amount of data as you originally had, because that data then has to be sent to the workers as well. This is always going to be true with the Snow backend, and it is often ends up being true with the multi-core backend as well. Even though theoretically the multi-core backend lets you share memory with the master R session, but because of how garbage collection works in R, and because you're often creating and destroying objects, that theory doesn't always hold in practice. So one of the advantages of using some sort of file-based data structure is that we can easily share that between R sessions without needing to transfer a huge amount of data. So I'm going to talk very briefly in the time that we have left about a couple of file-based backends that are available on Bioconductor. The first one is something called HDF5 array that Cardinal doesn't currently use, but it could. And this is something that's used widely in the rest of Bioconductor packages, especially in the summarized experiment and single cell packages. I'm going to talk about Matter, which is the backend that Cardinal currently uses for working with larger than memory data sets. So this HDF5 array is based on another package called Delayed Array, which is a package on Bioconductor for working with large data sets. And the basic idea of delayed array is that any operations that you apply to a potentially very large matrix are delayed. So you can index a very large matrix and get a subset of it, but that doesn't actually do anything to the data until you actually want to do something with that data. That's the idea behind delayed array, as well as things like, say, multiplying or scaling the matrix. All of these operations are delayed and aren't actually applied until you actually need the data from that matrix. So that makes it much more efficient when you're working with large matrices. Matter is the package that Cardinal uses, and the idea behind Matter is that it provides a flexible framework for working with different kinds of binary files, where the IBD part of an IMZML file is one of the file types that is easy to access through the Matter package. And this follows some of the same ideas of delayed array in that certain operations, such as subsetting the matrix or arithmetic, so multiplying everything in the matrix by some value, or scaling the matrix, are delayed and are only applied when we actually access the data. Again, on Bioconductor for delayed array, a specific implementation of note is the HDF5 matrix class that is built on the HDF5 scientific data format. So I'm going to do this same example using both delayed array and Matter now. So most file-based backends have some kind of limitations on what kind of data they can represent. So here in my example, spectra is a mass spectra list. And if I see what this actually looks like, it's a list. It's an S4 class that is a list of a bunch of other S4 classes, each of which is a mass spectrum object. I can't easily work with this as it is using delayed array or matter. So I have to simplify this mass spectral list into something that is representable as just a simple matrix. So I'm going to just use a helper function from base R, simplify to array, to turn this mass spectral list into a matrix of intensities. So now I have a matrix of intensities, 500 spectra, 3,879 features. And this is something that I could work with as an ordinary matrix now, where each of the columns of this matrix is a mass spectrum. So in this example, I'm just going to use this HDF5 array package. So I'm going to load up the HDF5 array package. And I'm going to write this intensities matrix to an HDF5 file. So an HDF5 file is a scientific data format that can contain different kinds of objects. So I have to name what I want the name of this particular matrix to be inside of the HDF5 file. So I'm going to create a file called intensities.h5. That's my HDF5 file. I'm going to name this matrix intensity. Let me check where I am right now. Let me set a different working directory real quickly. I don't want to clutter up that. All right. Okay, so let me turn this into, I have one created from when I wrote this, so let me get rid of it. All right, so now let me write this to an HDF5 file. You can see moment, and now this intensity underscore h5, this is now an HDF5 matrix of type double. And so that means all of this data from this matrix is actually stored in an HDF5 file. You can see it right here in my folder. So this is an HDF5 file. So these intensities, these are all stored in the file rather than in memory. If I want to access one of the columns, I can still access it, and just that column will be loaded into memory. I'm going to plot this so I can see that column still looks like a mass spectrum. So it looks like that went correctly. All right, so the nice thing about working with these file-based data structures is that it's faster to pass them to the worker R sessions than if I had all of this data in memory, and then I would need to transfer that data to the worker R sessions. Here, all I need to do is pass the small amount of metadata that is stored in the actual object. So for example, let me see how big this intensities h5 object is. So the actual size of this object in memory in R is just 2.82 kilobytes. And the size of it on disk, let me see, is 13 megabytes. So if I were to process this data in parallel, I would have to transfer each of the columns to the worker R sessions, whereas here, all I need to do is pass this 2.28 kilobyte object, which just contains the metadata for where to find these intensities in the original files. So here, I'm going to iterate over the column indices. So here, intensities h5 has 500 columns. I'm going to iterate over those because these smooth noise, remove baseline functions expect a mass spectrum object. What I'm going to do in my BP lapply code now is I'm going to extract the column that's corresponding to the current mass spectrum and turn it into a mass spectrum object here. Again, I need to make sure that the worker R sessions have the MS-example package loaded. Now I also need to make sure they have this HDF5 array package loaded. And so I don't remember what the current backend is. So let me see what the current backend is. I can spell BP param. All right, so I'm currently using the serial param. Let me register multi-core param, so this is a bit faster. And let me run this again. So now I am processing these spectra in parallel, but rather than BPLApply having to transfer the actual spectra data to each of the workers, now I'm just passing the metadata in this intensity H5 object, and the spectra are being loaded on each worker directly. Also in this case, since the data is on disk, the file, there is a file-based I/O here. So overall, this is going to be a little bit slower than when I had all of the data in memory, but it is very memory efficient. So if this data set were larger than I could fit into memory, I could still do this without running into memory issues. All right, and then let's do the same thing using Matter. So here I'm going to load Matter. And so Matter is just, so works in a similar way. So here I can just use the as.matter function for Matter to coerce my original matrix of intensities into a Matter matrix. These will automatically get written to a temporary file, since I didn't specify any files. So now all of this data is stored in a temporary file here. If I wanted to, I could decide where I wanted that data to be written. But the same idea applies. The actual size of this object in memory is just 13 kilobytes in R, but the size of this memory in the file is 15.5 megabytes. There's a slight discrepancy here versus HDF5 because HDF5 does some compression, whereas Matter will just write things to a raw flat binary file without doing anything. That does mean that Matter can be a bit faster sometimes since it doesn't have to worry about decompressing anything. So we can access columns of this just like we would an ordinary matrix. So here I can access the first column. If I want to plot this first column, I can see, again, that still looks like a mass spectrum. So everything seems to be working. And if I run this again, now using the same strategy, but now using this Matter matrix, and the result returns quite quickly actually here. So let me plot, say, the first result. I can see that was some sort of processed mass spectrum. So again, the file-based I/O here is slower than if all of the data were in memory. But because we're only loading the data when we actually need it, this is going to be very memory efficient, and this is a way of working with larger than memory data if we can't actually load all of it into memory. So last thing I want to talk about kind of goes back to what Cardinal is actually doing with these processed imaging experiments. Or actually, wait, are we? Oh, we stopped at 2.
A bit over time, but I think you can do that. It's okay.
Okay, for a moment I thought we were going to 2:30 instead of 2:15.
We can do that.
All right, so if everyone wants to bear with me a tiny bit longer, I'm just going to kind of go over briefly what's actually happening under the hood with these processed imaging experiments. So one cool thing that Matter allows is it lets us do this on-the-fly binning when we have mass spectra that have a different list of MZ values for each spectrum. And I can demonstrate that right now here. I'm just going to use this MS example package to show you what's happening under the hood. So I'm again going to replicate, I'm going to simulate some mass spectra. So now spectra 2 is again a list, this time a regular list of different mass spectra. And each of these mass spectra now has a different list of MZ values associated with it. So here, for example, you can see that the MZ range for each of these different 100 mass spectra has a slightly different MZ range. In fact, if I see how long each of these different mass spectra are, I can see that the first one has 4,300 data points. The second one has 3,500 data points. So each of these mass spectra have a different length. And if I look at the actual MZ values here, I can see that they have very different MZ values associated with them. So one thing that Matter allows is it lets us do this on-the-fly binning so that we can map mass spectra that have different MZ arrays to a common MZ list. And that we want to do that in Cardinal because we need to be able to quickly index into the rows of the matrix so that we can create images. Sometimes that's not as fast as we'd like because of how IMZML is stored, but it is a way that lets us reconstruct the image without easily. So here I'm going to create a Matter object from these MZ values and intensity values. So these are now, this is now a list of MZ values. It's an out-of-memory Matter list. So all of this list of MZ values are now in a file, a temporary file somewhere, and the same is true for these intensities. What I can do now is first, before I show the on-the-fly binning, I can actually just iterate over these two separate lists like I have been doing before. So this allows us to work with these different mass spectra exactly as they are without having to put them into a matrix at all. So here I'm doing the same kind of BPL apply strategy I was before, passing the indices and extracting the corresponding intensities and MZ values from this list, from these file-based lists, reconstructing my mass spectra and doing the pre-processing on it. And again, this should run quite quickly because I only have 100 of them now. And if I plot one of these, yeah, that looks good. So what's happening in Cardinal is, in order to be able to represent the data as a matrix at all times, we put these into a Matter sparse matrix. And so in Matter, a sparse matrix can have keys associated with the data for each of the columns. And so in the case of processed MS imaging data, the keys are the MZ values and the intensities are the values. The thing that makes this different from an ordinary sparse matrix is that, of course, we need to bin these on the fly. So each row of this matrix can be allows for collisions. And when we have a data point in a mass spectrum that matches to or a row in this matrix that might match to multiple MZ values in the raw spectra, we can bin them together, in this case, just by summing them, but we could also take the mean or the maximum value or really whatever we wanted to. So here I've created a sparse matrix of these, and I can see the key values. So this is the kind of the canonical list of MZ values associated with the entire matrix. So all of the spectra that originally had individual MZ values associated with them will now be binned on the fly to this canonical list of MZ values. And so if I wanted to, I can very easily say, apply over the rows here to get, say, the mean mass spectrum. So here, this would give me mean. Say I want to plot this. So this is what the mean mass spectrum looks like as an example. And that's something that we couldn't do as easily if we weren't able to represent this as a matrix and apply something over the rows. All right, so that kind of wraps up the last thing I wanted to show. And again, this is what's going on under the hood in Cardinal with these MS image processed experiments. So I hope some of this was useful. I know there are a lot of questions on Cardinal, but I wanted to provide some kind of general information about working with large data in parallel that can be useful both with Cardinal as well as things like MSNBase and any bioconductor package. So hopefully this was helpful. Again, all of the material is available online if you go to the corresponding vignettes or GitHub pages. Thanks.
Well, thank you very much, Kylie. Again, a very big virtual round of applause for you. And thank you very much to everybody who stayed on until the very end. So this is technical material. I realize it's difficult sometimes to follow. So it is very nice to see that so many of you stayed on. So I'm guessing Kylie can stay a little bit longer in case you have questions, but maybe before that, let me also thank Laurent and all the previous speakers so far. And let me also share with you that tomorrow we have a very special program. We would like to give a platform for contributed presentations. So these are participants who are going to be here in person and present their work on developing computational methods for mass spectrometry, proteomics, imaging mass spectrometry. And even though we cannot meet in person, we would like to give this platform to them tomorrow. So please come and support them. And thank you very much for joining us. And so we'll stay on a few more minutes in case you have questions to Kylie regarding Cardinal or regarding scalability or anything else. And if there are no questions, then we'll just stop here. Well, thank you very much.
Thank you. So if there's any kind of technical questions, I'd be happy to answer those now. If there's any more general questions about help with Cardinal, refer you for now, at least, to the Cardinal Google Help group, which there's a link to that on the materials for today. What's the fastest format for pulling a data set from disk into memory? So the fastest format for reading data into memory, that depends a lot on exactly what kind of data you have. If it's data in a very specialized format like mass spectra, then you're somewhat, well, if you want to actually share that data with other people, then you're kind of stuck with the acceptable formats for that kind of data. If you don't need to share that data with other people, or you don't mind other people having to do a little bit of work to read that data, then there are a number of specialized file-based formats that are very fast just for that are kind of designed for just that purpose. Things like, there's a lot of work in Python for things like this. I think some of the names are things like Feather, Parquet. These are kind of specialized formats for reading data directly from disk very fast. But if you want something that might be more useful when working with data in Bioconductor, then something like this HDF5 array might be more useful. The nice thing about HDF5 is it's an open scientific format that many other scientists might be able to use a little bit more easily. It also gives you more flexibility in exactly how you store it. Again, matter is another option, but it just is essentially just is a list is flat raw binary files. So it depends a lot on your use case and whether you're just doing this for your own data sets, for when you're working with your analyses on your own, or whether you also need to share these data files with other people. And then there's also whether you're counting conversion time as part of the time spent. Question on co-registration. Currently Cardinal doesn't have a co-registration method built into it. That's something that we're working on right now. So co-registration with, say, microscopy image is something that we're working on, but we don't have available right now. All right, I think.
Okay. Yes, I
think we'll call it a day.
Oh, one more.
I'm going to defer this question for now, since I think it's a little bit more in. The question is on sample preparation, and so that's going to be a whole other statistical experimental design topic that I'm not going to be able to answer in 5 minutes here. Maybe for next year's May Institute. And a question on UI. I'm assuming it means a GUI, graphical user interface. There is currently a Cardinal Viz GitHub repository. If you look for me on GitHub, there is a Cardinal Viz that you can install from GitHub that uses a Shiny interface. It's still under construction, so if you run into bugs, don't complain about them yet, because it's something we're still working on. I don't have an exact timeline for when that will be ready. Using an interface with R running in the background, that's harder because any user interface that we provide, we are probably going to rely on Shiny for that. So having R running in the background without locking the R process until the Shiny app is done, that would have to be something that comes from the Shiny people rather than something that I could do. All right, I'm gonna.
Thank you, Kylie, very much again. Now. Thank you for the great presentation and for answering all the questions. Thank you so much.
All right, stay well, everyone. Have a good day.